All right, we are going to carry on from question 4. One purpose of the coolant in a thermonuclear reactor is to maintain a safe working temperature within the core. State the other purpose. So what happens is, oh, there we are. So what normally happens is inside the actual nuclear reactor core, the reaction is taking place. There are coolant tubes that are pumping the coolant around the reactor, cooling it down. It comes in cold and leaves hot. Yeah, it's carrying the heat away, and that coolant goes to another heat exchanger, which passes the heat that it took from the reactor into water, and that water turns into steam and takes part in the normal power station stuff. So it's that steam sent to a turbine. The turbine spins a generator, and then generator creates current. So that's one. I checked the mark scheme, and it says absorbing neutrons as well, but that's kind of a weaker reason. State two properties that engineers consider when choosing a liquid to use as a coolant in a thermal nuclear reactor. So based on what we know, the specific heat capacity is definitely important because it determines how much energy it can carry. So I would think that well, deciding specific heat capacity is a different story. You have to kind of think about this heat exchanger and this heat exchanger, but that's more of an engineering domain problem. Okay, I'm not gonna get distracted by that. Specific heat capacity. Another thing is how easy it is to flow. So viscosity would be another one. I'm sure there are a few more in the mark scheme, but I'm not going to deal with those because those are the ones. These two are the ones that are immediately kind of obvious. Explain how the power output of a thermonuclear reactor is decreased. So in a fission reactor, I'm going to pause the video really quickly for this. Yeah, so let's take a look at this. Basically, it's the same old GCSE level stuff of we have a lot of neutrons. Sorry, we have a lot of uranium atoms. We shoot a neutron leading to a chain reaction. That chain reaction inside here is controlled by this, well, control rods. When you fire neutrons, the chain reaction begins, as you can see over here in this zone. The temperature is starting to rise. And to kind of control it, you send the control rods in. The simulation doesn't really show it very nicely. Anyway. Yeah, let me pause that really quick. So a nice way to write this would be control rods are moved into the reactor, and these absorb neutrons. Remember, it's the neutrons that do the chain reaction, right? Controlling the chain reaction. Right, here we have a gravitational question. Most of you had no issue with this. Feel free to skip ahead. Orbital angular speed, again, we're using the omega TF structure. that I taught you in circular motion, omega, and t, we're looking for this connection over here. We have omega is 2 pi over t, and this value over here is actually wrong. You are getting something close to, I think, 2.6 into 10 to the power something minus 7. Let me, yep. So what happens is it comes out to around 2.66 10 to the power minus 6 radians per second. Right. Then this figure shows the Earth, Moon, and a point S1. Distance from the center of the Earth to S1 is given. Center of the Earth, center of the Moon, and S1 are in a straight line. Satellite S1 is in a circular orbit around the Earth. The satellite has the same angular speed as the Moon. Centripetal force on the satellite is a combination of the gravitational force from the Earth and the gravitational force from the Moon. Magnitude of Earth's gravitational field strength at S1 is given, and we need to find the magnitude of Moon's gravitational field strength. So gravitational field strength is very straightforward. G equals gm over r squared. It's a matter of calculating it. And that would be 6.67 into 10 to the power minus 11 into 10 to the power, where's the mass of the Moon? Huh. Why isn't the mass of the Moon given? That's very weird. Poorly designed. Looking at the next question, they've given the mass of the Moon here. Distance from S1 to the center of the Moon. Interesting. Angular speed is known. Okay. So we knew the angular speed of the Moon. The satellite has the same angular speed as the Moon. So from angular speed, which is this one, we can figure out the centripetal acceleration, which is the total gravitational field strength. And then from that, I think we can figure out how much of that is due to the Moon, because we know how much of it is due to the Earth. So let's go ahead and do that. That means this is not the approach. We need to look at A equals omega squared r. This is 2.66 into 10 to the power minus 6. The total spinning radius, this one over here, is 4.489 10 to the power 8. So we have an idea that the total centripetal acceleration of the satellite is, let me calculate that quickly, 10 to the power minus 6 to, what was it, 4.489? Yeah, the distance, because I'm just looking at it as a circular motion. I'm not even thinking about the Moon. I'm just interested in the circular motion and the centripetal acceleration required to sustain that. 9, 10 to the power 8. Oops, forgot to square the omega. Okay, I'm getting 3.176. The total centripetal acceleration required to sustain that circular motion is 3.176 into 10 to the power minus 3. Now, this would be either newtons per kilogram or meters per second square. It doesn't matter. It's just an acceleration. Out of that, 1.98 into 10 to the power minus 3 is due to the Earth. So how much the remaining amount is due to the Moon. So what I'm going to do is the 3.176 into 10 to the power minus 3. That's minus 3. Subtract the gravitational field strength over here at S1 due to the Earth, which is 1.98 10 to the power minus 3. And that gives me the difference, which is should be coming from the gravitational field strength of the Moon. When I plug that into my calculator, I get, hold on, 6 minus, that is 1.196. Minus 3 newtons per kilogram. Let's check that. Yeah, so it looks correct. I'm going to move on. Calculate the distance from S1 to the center of the Moon. So here, the gravitational field of the Moon, let's draw roughly here. That looks very ugly, but you get the idea. Gravitational field of the Moon, this is the radius. So over here, we know G. If we use the equation, we have been given the mass in that question. We can figure out R because we know this you can figure out R. R equals capital GM over simple G. Now we use 6.67 10 to the power minus 11 into the mass that's given. I'm not going to write it. It's this one over here. And the G is 1.196 10 to the power minus 3. Calculating it, 7.35 22 GM. Oh, remember this is R squared, isn't it? I just remembered. Earlier I wrote some nonsense. This should be squared. Or bad. That means after getting the answer on the right side, we need to square root it. Right. That's oops. Square root. I'm ending up with a distance of 6.4 into 10 to the power 7. I'm gonna put some more significant figures. Yeah. To the power 7. Yes. Does that make sense? To the power 8 compared with that, this is 10 to the power 7. Sort of makes sense, yeah. You can check with the mark scheme later. Figure 8 shows the Earth, Moon, and a point S2. Now that means the examiner has completely forgotten about the satellite, I think. These are in a straight line. Satellite, okay, this is a satellite, but instead of being over here, now it has moved here. Circular orbit around the Earth. Satellite has the same angular speed as the Moon. So that, oh, it's a different satellite for sure, isn't it? Oh, okay. Okay, it's a different satellite in a different orbit. But anyway, that doesn't matter. Satellite has the same angular speed as the moon, so that the centers of the Earth, moon, and satellite are always in a straight line. Explain how the resultant force due to the gravitational fields of the Earth and the moon cause the satellite to orbit with the same angular speed as the moon. No calculations are required. Even though they say no calculations are required, I think here we need to understand something. So, if we use gravitational force 3mr squared, hold on. No, actually, we don't even need that. If we use A equals omega squared r, I think it makes it very clear. Give me a second to think. Okay. Yes. So omega equals centripetal acceleration divided by r square root, right? Now, what we can see is that in order for omega to be constant, when r decreases, like this ratio of acceleration and radius should be constant. That means a and r should have a constant ratio between them. So what is that telling me is that interesting. I have to think about this a little bit. Satellite S2 in a circular motion around the Earth. Satellite has the same angular speed as the moon, so that the centers blah blah blah. Explain how the resultant force due to the gravitational fields of the Earth and the moon cause the satellite to orbit with the same angular speed as the moon. Calculations are required. I think in this case, this is not telling me anything interesting, because the radius of S2 is smaller, and I know that, okay, even if the Earth was the only object exerting gravity, okay, hold on, thinking, the gravitational field strength is going to be higher, right? Okay. Now we are getting somewhere. So let me explain my thought process here. Basically, for omega to be constant, this I'm going to replace this with a g so that you guys know what I'm talking about. It's the gravitational acceleration, which is the centripetal acceleration. That divide by r needs to be constant, but we know that since S2 has a smaller radius than the moon, this quantity is smaller. So in order for omega to be constant, g has to be smaller. But in reality, we know the closer you get to something, the stronger the gravity is. So what should have happened if the moon was not there? G would be higher, which would lead to omega being higher. In order for omega to be constant, that means the moon has to fight it, right? So this is an object at S2. There's this gravitational acceleration from the Earth, and we saw by analyzing the circular motion that if the gravitational field strength is only from the Earth, then when it's closer, what's going to happen is the simple g is higher. This number is going to be higher, which will lead to the omega being higher. So there must be some other gravitational field strength from the moon which is fighting it and making the gravity decrease by the same amount as the radius so that the omega can remain constant. So how can we explain this in words? Let's take a look. We can say we can say, wait, I'm thinking how to put this into words. Proportional to G. Yeah, I'm struggling to do it without calculation. So no calculations are required, but we can still use proportions, right? So that means without putting numbers. So I'm still going to use it. Omega equals root of gravity over r. Where did I get that? I actually got that from centripetal acceleration equals omega squared r. And for my decision making there, I use this circular motion structure that we normally use, right? Because I saw how is omega related to gravitational, acceleration. So omega equals root g over r. So so it's a for angular velocity to be constant, g and r have to increase or decrease proportionally. We'll say, however, S2 has a smaller radius I'm gonna just say that in words. Okay, S2 has a smaller radius around the Earth. Smaller radius around the Earth than the Moon. And a larger gravity so yeah, and a larger gravity than the and a larger gravity due to Earth. This tool is so annoying. A larger gravity due to Earth. So its speed would be okay. I'm kind of sick of this. I think I'm going to edit this out. Yeah, I'm going to edit it out. Sorry, where were we? Yes. So I'm going to start with saying this is equal to omega squared r. Omega is equal to square root of a over r. And then I'm going to make a little statement. I'm going to type this out. omega is to be constant, then acceleration has to be proportional to radius, say centripetal acceleration. Centripetal acceleration has to be proportional to radius so that a divided by r is constant. But the closer, no, but the smaller the distance from the Earth, the stronger the gravity. So A over R would be higher for S2 than for the Moon. Right? Therefore, in order to keep A over R constant, there must be something that makes the resultant gravitational field lower at S2 this is the gravitational acceleration of the S2, which opposes the attraction of the Earth. Right? I'm going to switch back to this software over here. I think I'll write in Microsoft Word. Okay, the electric potential at a point in the electric field is -4. So a lot of you said that, yeah, it's the work done per unit charge. I'm going to switch back to Word. So a lot of you said it's the work done per unit charge. That was, I think, 1 mark. Bringing a unit charge infinity to that point. Yeah. Energy at infinity is 0. That's the gravitational potential energy, okay? At infinity is 0. And Thinking. Work is done against gravity to get to infinity. Negative sign, yeah. Yes. Yeah. Energy at infinity is 0, and as work is done on the, oh my god, why did I say gravitational potential energy? I meant elastic potential, electric potential energy. Okay. Positive unit charge. Work done per unit charge, bringing a unit charge from infinity to that point. Ugh, disgusting. No, no, no. It's messed up. Scrap. Um, electric potential. Infinity to that point. Just from infinity to that point. Yeah. Electric potential, the work done per unit positive charge. Yeah. Bringing positive discharge from infinity to that point. So we can say minus 4.0 volt is this the work done by the field on the discharge was 4 joules. Yeah. And the negative sign indicates that the work was done by the field on the charge, and that electric potential energy at infinity is 0. Right. So, going back to the thing here. Figure 9 shows the variation of electric potential V with distance x between 2 points that are 700 nanometers apart. It looks like a wave, but it has nothing to do with a wave. It's just 2 points, and there's some weird, complicated charges in there that's messing with the whole thing. Determine using the graph in figure 9 a value for the maximum magnitude of electric field strength between the points. So here, what you're meant to use is the fact that E is V over D. So looking at this graph, voltage is the y-axis and distance is the x-axis, which means we are looking at gradient. So what you're meant to do is to draw a tangent to the graph over here. Yeah, tangent to the graph over here. Use that tangent with a ruler. Use that tangent to find the gradient of the tangent. When you're using a graph to find gradient, make sure you pay attention to the units, because you can see here this one is not a SI unit. You need to convert it to SI units, otherwise you're going to get a wrong answer. Electron is at x equals 100 nanometers. It has sufficient kinetic energy to move to x equals 350 nanometers. Determine the kinetic energy lost by the electron moving from x equals 100 to x equals 350. Energy equals, no, so voltage equals energy per unit, some kind of charge. So change in voltage means change in energy, because charge is constant. Yeah, so what we need to do is Q times delta V. Change in electrical energy is Q times delta V. That is 1.6 into 10 to the power minus 19 times, you just have to get it from the graph here, at 100 and 350. 100, the potential is minus 0.2. At 350, the potential is minus 3.4. So minus 3.4 minus 0.2. The difference there, 3.4, 0.2, okay. Wait a second. The difference, yeah. The difference between these two values is 3.2, isn't it? It should work out to 3.2. Yeah, don't worry about the overall sign. What you're interested in is basically the difference between this this and this. You're basically interested in that difference over there. That's 3.2. Should work out to that. And when you calculate, that gives you 5.12 into 10 to the power minus 19. Different electron is initially at rest at x. The electric field causes the electron to start moving. Discuss the motion of this electron due to variation in electric potential shown in figure 9. Let's figure it out. Before we start, V is equal to minus, yeah, I'm used to that format, so minus 1 over 4 pi epsilon naught. Yeah. Sorry, give me a second. 4 pi epsilon naught Q, which is the charge Q, and a little charge, simple Q. The big one is capital Q over R. So the fact that this voltage here is negative at 150, right? 150 nanometers means over here. The fact that it's negative, whatever 0.5, but the fact that it's negative tells me that we are dealing with a positive charge in the middle here. Sorry, what I meant is we are dealing with the field of a positive. That's not the best way to explain it, but if you put a plus there, you would have repulsion, but if you have an electron, you'd have attraction there. It's very interesting to think about. But let's do the question. Like which direction the electron will start to move, basically. That's the key thing. Interesting, interesting, interesting. Okay, so we are right here. So is it going to move this way towards 200 or this way towards 100? That's the key thing that I want to answer there. But for this now, I'm having trouble kind of figuring out what kind of uh, charge arrangement will lead to this stupid, voltage curve. So I'm just going to compare to what I know, which is having a positive Q and a positive simple Q. So what do I actually know is that if you take some lines like this, if you take some lines like this, the V over at A and the V at B, if you compare them, it's V equals KQ over R minus. What I do know is that over here, since the radius is higher, it's a smaller value. Okay, since the radius is higher, it's a smaller magnitude, still negative, but a smaller magnitude. So I know that a positive just charge placed at B will move towards A naturally. That's a natural tendency to repulsion, right? Plus and plus, same charges repel. So it's going to go this way. If I put an electron here, it's going to come this way, attraction. And it will seek out a point where the voltage is, the R is smaller, V is higher, the magnitude is higher, still negative. So I'm looking for the same pattern over here. If I look at this graph, if you go down here, what's happening is, it's higher. Is higher. Interesting. So, I mean, my logic tells me that it will move towards the 200 side. I'm going to pause and quickly check the mark scheme. I just looked at the mark scheme and I don't agree, because what they're saying in the mark scheme is that initial direction of motion is towards the left, which is 100, this side. But I can see that if we are going that way, then the magnitude of the electric field will reduce. Now, looking at this logic, I know that EA is a negative value, but I'm just talking magnitudes here, right? Magnitude is going to be less than the magnitude of the potential at B, because it's inversely proportional to radius. So that doesn't work for me, because it's a bit mad. The magnitude of I know that the positive charge will move that way towards a lower magnitude. But what the Edexcel examiners are trying to say here is that the negative charge, the electron, will also move over there. So my current understanding doesn't tell me why it will move this way. Or a negative will seek out stronger, like a higher magnitude. Huh. So yeah, I'm gonna skip this one, because honestly, my understanding tells me that it will move the other way. Sorry, I mean the AQA examiners. So I'll have to think about that and link ideas about maybe it has something to do with gradient. Not quite sure. Or what if we think in terms of the electric field strength? What will that work? Because the electric field strength is the gradient here. Oh yeah, the electric field strength is a gradient, and the gradient is negative, isn't it? So gradient is negative means electric field strength is having a negative charge. But still that doesn't say anything. So yeah, I'm gonna skip this one for now and think about it. You guys have the mark scheme, so you can check. A team of students uses 900 dice, each with N sides, to model the decay of a radioactive material. Each dice represents a single undecayed nucleus. Throw of the dice represents a constant time interval. Okay. When the dice are thrown, those that show 1 represent decayed nuclei and are removed. Students count the number of N undecayed dice that remain. The procedure is repeated using undecayed dice. Explain why N has been plotted on a logarithmic scale. So I saw many answers like said that a logarithmic scale, it turns the exponential curve into a straight line. Yeah. Other answers that were converts the exponential curve to a straight line. Other answers, let me check. The answers that were accepted were allows trends across a large range of data to be seen on a reasonable size of paper. Yeah. So logarithmic scales are normally used to make like huge ranges of data fit onto a piece of paper when you're dealing with like a very, very large range. Otherwise, the graph would be really huge and it wouldn't fit on the paper. In this experiment, a decay constant lambda can be defined that models the radioactive decay constant. Determine lambda. Go on to show that your value, go on to use your value for lambda to show that n equals 4 for the dice used in this experiment. Let's take it out. See what you can use. Let me get the equation sheet and check in nuclear. Yeah, what we have is we have the activity, sorry, we have the radioactive decay equations, exponential decay equations. We also have the half-life equation. Let's see, lambda. Lambda appears, lambda is T half. Yeah. So from half-life, so you're looking for lambda, right? Lambda appears in a couple of equations. One is equals m naught e to the power minus lambda t. And the other one is lambda equals half-life. The most straightforward one here is, I think, this one, the half-life. So I saw, I think it was Nihal who had tried to get the half-life, but there was some error, or Moise, I can't remember for sure. But to go from 1000, half of 1000 is 500, right? They had looked somewhere here, but actually 500 is over here. So 100, 200, 300, 400, 500, 600, 700, 8. That doesn't make sense. Let me check. 100, 200, 300, 400, 500, 600, 700, 800, 900. What? I'm blind. 200, 300, 400, 500, 600, 700, 800, 900. Oh, this top one is 1000. Okay, so we are starting at 900. So we are looking at 450. This is 200, 300, 400. This is 500. This is 450. Going over there, we are looking at a point somewhere over here. And the time corresponding to that is 2.4. Yeah, 2.4. So this would be N2 over 2.4, which is equal to 0.288. Typical radioactive source used in schools has an activity of 100 kBq. Radioactive source used in hospitals has an activity of 370 GBq, giga. State one safety measure using radioactive source in a school lab. We want to discuss how this safety measure needs to be adapted for safe use. So there are a couple of safety measures. Unfortunately, what I saw in the papers that I corrected was the use of goggles. Goggles isn't going to do anything for you, okay? Because if it's a alpha source, anyway you are safe. If it's beta or gamma, if you pointed at your eyes, you're already done, and it passes through the goggles. Okay, so normally you use tongs to keep, like, hold the radioactive source. The radioactive source itself looks like this. This is the cross section. The radioactive thing is inside over here, and this is made of metal so that the radiation escapes in this direction. So you point it away from people, and you use tongs to hold this over here. I'm not sure why. Maybe there's a, yeah, because it could, maybe there's a slight risk of some low energy radioactive particles coming out on this side. Maybe that's why they use tongs. But in GCSE, what we learn is we use tongs because, yeah, we use tongs, hold it away from people. What else? Yeah, that's normally it. So if I say use of tongs, in school lab, how to adapt that for the hospital? Maybe leave the room. Sorry, this is really annoying me. The tool, yeah, for hospitals, you'd have to adapt it like that, or maybe use a robot to control it, something like that, where you are not in the, even in the range. X-rays are a form of ionizing radiation. Person has a checkups with dentist every 6 months. Dentist takes X-ray images when the person has reported a problem. Suggest why. Maybe you can write some answer related to like this, because the examiner has put ionizing radiation, right? Maybe you can say ionizing radiation causes cancer. Increases the risk of cancer. So it is not safe to do it periodically. It's not safe to do it every 6 months because that will increase the risk of cancer. I'm going to check the mark scheme to see what they're saying here for this one. Okay, causes mutation, that idea. Then comment reflecting the balance of risk and benefits when a filling is required. Okay. Okay, end of section A. Interesting. Question 8. In which process is work done by an ideal gas? Let's see. Work done equals force times distance. I think in your equation sheet, they've already connected it to pressure into volume. Let me just double check. Thermal physics. Okay, no, they haven't. So the idea is that force divided by area multiply to area, so that these two cancel out to distance, and this one becomes volume. Okay, so, and this is pressure. So overall you end up with the idea that work done is equal to pressure into change in volume, or change in pressure at a constant volume. Or in the case of a graph, any combination of the two, right? Any combination of the two, as long as you have an area under this graph, there's work done. Let's take a look. Doubling the pressure at a constant volume. Yes. Doubling the volume at a constant pressure. Oh, hold on. We have a small problem there though. Okay, I think something I said here doesn't make sense. I'm going to delete this one, because remember that if you don't move, if there's no distance in Distance travel, if there's no displacement, there's no work done. So I don't think this can work. I'm kind of remembering it vaguely from university, but I think I may have made a mistake there. So let's forget about that idea. Doubling the pressure at constant volume won't work because there's no displacement. Doubling the volume at constant pressure, yeah, that would do the job. Doubling the temperature at constant volume, see, again the thing is constant volume. If the volume is constant, there's no displacement, so no work done. Doubling the pressure at constant temperature, again there's no idea of a displacement, and that's why that's not the answer. Looking at number 9, molecules have speeds 2, 4, 5. What's CRMS? Remember that C, root mean square, is the root of the mean of the square, is the root of the mean of the square of the speeds, right? Dot, dot, dot. So here, if you have only 3 molecules, what you would do is 2 squared plus 4 squared plus 5 squared divided by the number, which is 3. This is 4 plus 16, 20. 20 plus 25 is 45. 45 divided by 3 is 15. And the square root of 15 is 0.87. Okay. Ideal gas is enclosed in an insulated container with a small electric heater. Initial temperature is given. Product of pressure and volume is 5000. The gas expands at a constant pressure and does 1660 joules of work. What is the final temperature of the gas? Okay. Work done is equal to pressure times change in volume. So, okay, pressure and volume. Okay. So what this is telling me is this is PV2 minus PV1. This is delta V. The work done is 1660. Initial product of pressure and volume is 5000 minus some amount here. 1000 minus does work. It does work means the final value has to be, hold on, thinking. If it does work to some outside thing, its energy has to reduce. So the number over here that I'm looking for has to be smaller than 5000, isn't it? That's my logic there. So maybe I put this in the wrong order, right? Maybe 5000 is here, but anyway, the answer that I'm looking for should be less than 5000. So I'm going to do 5000 minus 1660. Telling me that the final PV value is going to be 3340. Now, final temperature of the gas, pressure, volume, and temperature. We are dealing with a big gas, so macro equation. PV equals NKT. Okay, but I don't have N. So when I have too many unknowns, N and T are both unknown, that tells me I need another equation. That means I may have to write this PV twice. So first time I'm going to write for the initial state of the gas, that's 5000 equals Nk into the 300, which was the temperature. Now 3340 equals Nk into new temperature. And solving this equation 1 and 2 simultaneously, what do I get? I'm going to do that over here. T divided by 300. This one divided by this equals divided by this 3340 divided by 5000. which tells me that the temperature is 100, which is not the answer. That's bad. So let's backtrack. Electric heater. Oh, there's a small electric heater. I forgot about that. Pressure of the gas is this much. Product of pressure 5,000. Gas expand constant temperature. Interesting. It expands. Oh, it expands. The pressure is constant. Temperature should have increased because the volume has increased. That means pressure and volume is bigger. Okay. So what's happened is my logic here is flawed, right? The logic here that I was explaining, like it has to be smaller than 5,000. No, in fact, it has to be bigger than 5,000. So this has to be plus, which means PV is equal to 6,660, which means that this number has to change 6,660, and this number has to change 6,660, which means temperature is actually 399, which is 400. Better if I check this in the mark scheme, yeah. But anyway, I prefer that challenge of not looking at the mark scheme. If any of these are wrong, please let me know. Next lesson we'll deal with that. An air-filled parallel plate capacitor and a resistor are connected in series across the terminals of a battery. The plates of the capacitor are moved further apart. This change results in, let's take a look at what's happening here. Cell, resistor, capacitor over here. Okay. Plates of the capacitor are moved further apart. What does that do to capacitance? It reduces the capacitance because C, that's the equation. I think you can find it there. Yeah, C is inversely proportional, blah, 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 something in the top, and D, inversely proportional to D. But basically, when you increase the D, C decreases. How does that relate to this? Let's take a look. So let's say now, after connecting it, the capacitor would have got charged with some charge Q, right? Now we need some equation connecting Q and C, and what I can think is Q equals CV. So what's happened here? Q is Q and V, Q and C, E and C. Okay. Look at these answers. Decrease in the potential difference across the capacitor plates, decrease in the charge held on the capacitor plates, increasing the energy stored on the capacitor. Hold on. Thinking. Okay. Right. From what I know, when you change capacitance of something, what's going to happen is it changes the voltage across it instantaneously on an instantaneous basis, which causes charges to flow. But after that, the current stops flowing. Whatever, because you know that charging and discharging, the current versus time graph, it goes like that for charging and discharging. So ultimately the current is zero, which means that ultimately the voltage across the resistor drops to zero, which means this full voltage of the battery acts across the capacitor. So there's going to be some temporary instability in the circuit when you do this, but eventually it will settle to the point where the capacitor is once more charged. Sorry, as in the capacitor is at the same voltage of the battery, right? After it settles down. So I think ultimately voltage remains constant here because it's ultimately settles to the value of the battery. But Q is proportional to C. C has decreased. So I think decrease in the charge held in the capacitor plates is the ultimate result. Like temporarily, now, when as soon as you make this change, Q is has not started to change yet. So if you look at V equals Q over C, you'll find that when this drops, this becomes bigger. So I think current would start to flow the other way temporarily, but then ultimately the voltage across this will settle to the voltage across this. Kind of a harder question, you know. They're rare, but they occur in the other specifications as well. There was once a question in Edexcel about a capacitive microphone that was like this. Kind of interesting stuff. If you're interested, search capacitive microphone. Which change will increase the efficiency of a transformer? Increasing the thickness of the iron layers in the laminated core. Now, those iron layers in the laminated core, I'm just reminding you, this is a transformer, primary coil, secondary coil, and here we have the transformer core, which is made of iron. This is not made of solid iron because there are some things called eddy currents, some currents which are flowing inside here. So to reduce the effect of that, what they do is they make it out of laminated sheets of iron. Okay. If you increase the thickness of iron layers in the laminated core, it will increase the eddy currents, which will lead to a heat generation inside the core, which will decrease the efficiency. So that's not an option. In decreasing the frequency of the AC input voltage, frequency of it. I'm not too sure about that. I'm going to think about that. Move on to the next one. Decreasing the diameter of the copper wire. If you decrease diameter in the copper wire, resistance is equal to rho L over A. If I decrease the diameter, I'm going to decrease this and increase the resistance, which will cause more heating, and that will reduce the efficiency. So this is not an option. Increasing the distance between the primary coil and the secondary coil, that will actually lead to losses because the magnetic field has to transfer from the primary coil side to the secondary coil side, right? Through this iron core, the magnetic field has to transfer and cut the secondary coil. That's not going to happen. Sorry, it will still happen, but it will make it less efficient. Now, that leaves us with this answer here. So the logic here is that higher frequency means that the electrons are kind of moving this way and this way much faster. So the faster they move, the more they bump into the atoms inside and the more energy, heat energy they release. So if you decrease the frequency that the electrons are like oscillating, that would mean less heat loss. So I think this is the answer. You check with the mark scheme. Signal generator supplies a sinusoidal root mean square voltage of 7. It's replaced on oscilloscope screen, the tallest waveform. So it's the same amount of volts, but you want the tallest complete waveform. So let's take a look. Blah, blah. Tallest waveform. So if you have 1.5 volts per division, I'm going to just take some, value. Let's assume like 4 volt. If it's 1.5 volts per division, that will be around 3 divisions. If it's 2 volts per division, it's going to be 2 divisions high. The amplitude is going to be 2 divisions high. If it's 2.5, it's going to be less. So yeah, if it's 3 volts, it's just going to be a little bit more than 1 square. So if I want more squares here, I think it makes sense to have this one. Two signals have the same frequency simultaneously on the oscilloscope. Which one shows the frequency of both signals and the phase difference between them? Frequency we figure out using time period, because the x-axis is time. So time period is, I'm going to look at this curve over here. So the time is from here to here, which is 1, 2, 3, 4, 5, 6, 7, 8 squares, 8 divisions. If each division is 5 milliseconds, 8 times 5 is equal to 40 milliseconds. F is equal to 1 over t, which is 1 divided by 40 into 10 to the power minus 3. which gives 25 hertz. So I know that these are definitely not options. Phase difference. Hopefully that's okay. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 5 is 40. Okay. Yeah, that's fine. Phase difference. Let's figure out the phase difference. Comparing. What can I compare here? Peak, trough, trough. I can see that they are kind of half a square apart, aren't they? Even here they are like, it's not exact. That makes me worried. Let's see, look at the answers, see whether they're very different. Okay, they are very different. So I think we can gamble a bit. Yeah. So approximately half a division apart. Compare this and this distance over here is about half a division apart. Half a division corresponds to about 2.5 milliseconds. So what I'm going to use here is the ratios, right? Okay, yeah. So 2.5 millisecond out of the total cycle length, the time period of 40 milliseconds. So I need to know how much out of this 40 milliseconds time period corresponds to 2 pi. I need to know what is this theta. So it's a kind of a ratio thing. Solving that, let's see, theta into 40 equals 2.5 into pi. So theta is equal to, in the calculator, 2.5 into 2 pi. Just going to ignore the pi because it's here as well. 2.5 into 2 divided by 40. So 5 over 40. Closest answer is 125, which is close to 0.15. I'm going to go with this answer. This one I'm really curious about, so I'm going to actually check in the mark scheme. 14, 14, 14, 14 is D. Yeah, that's correct. Okay. Transmission cable consists of many strands of wire. Electrical energy is transmitted along the cable at a frequency of 50 Hz, which change gives the largest increase in efficiency of the electrical energy transfer along the cable. Let's see. Efficiency of electrical energy transfer. Okay. The largest increase in efficiency. Damn it. If we double current, now the logic here, as I explained on Saturday, is that, power is equal to current into voltage. So if we increase the voltage, the current decreases, and a lower current, because of P equals I squared R, when you reduce current, the heat power lost by the wires decreases. This is the standard explanation since IGCSE. GCSE. So doubling the current will actually decrease the efficiency. That's not an option. Halving the resistivity of the material of the wires, that's going to make resistance smaller, okay, by a factor of it'll make the resistance halved. So the power lost is going to become half of what it was before. So I'm going to write that down. We are going to have half the power loss for option C. Halving the number of wires in the cable. If we reduce the number of wires in the cable, we are reducing the cross-sectional area by half, aren't we? Because if you have, let's say, these are the wires in the cable. If the more wires there are in the cable, the bigger the cross-sectional area is. So if you halve the number of wires in the cable, looking at the resistance R equals rho L over A, if this becomes half, resistance becomes doubled. If resistance doubled, the power loss doubles. So it's actually going to make more heat power get lost. So this one is definitely out. right? It doesn't, it decreases the efficiency. Now, if you double the transmission voltage, if you double this, the current is going to halve. And that half factor is going to apply to this current and it's going to get squared. When half gets squared, it becomes 1/4. So the power lost is going to become 1/4 of the power of option A. So if you look at the power lost, this one has the less amount of power loss. So this one will have the greatest decrease. The power loss becomes 1/4. That means the power lost has become 1/4 of the power lost before. The efficiency gain is more rather than having the power loss become 1/2 of what it was before. Electron enters a uniform magnetic field at right angles to the field. Flux density is P. Circular path. Circuits completed by the electron in 1 second. 1 second. Number in second is frequency. So this one is actually a kind of a standard proof. What we have is circular motion. In a circular motion, our standard strategy happens to be the centripetal force. Yeah. So here the centripetal force is BQV because it's this is electron, right? The magnetic force, centripetal force is the magnetic force. So mv squared over r equals BQV, which means cancel this out, we get mv r equals BQ. Now we have to somehow, now this proof is a very specific proof that's normally there in turning points topic in AQA and particle physics topic in edXL. It's a very specific proof. So once you've gotten this, what you need to do is bring in some circular motion equations. Yeah, wait, hold on. Did I say circular motion? Yes, circular motion equations. So for that, we need the omega TF, C, V structure. And we need to bring F into it. And now we have V. So I'm thinking to connect them like this, right? Instead of velocity, I can put, let's see, V equals R omega, and omega is equal to 2 pi F. So V is equal to 2 pi R F. Yeah, bring that in. V is equal to 2 pi R F. So N times 2 pi F R equals Q. R and R get cancelled. F is equal to BQ over 2 pi M. BQ over 2 pi M. BE over 2 pi M. It's that. Very, very specific proof. This is following reaction occurs. What is the quantity of energy released? So here we have to look at the energy. So remember that equals mc square. This kind of question, you look at the mass on the left and the mass on the right. If there's a difference, that difference, which we call delta m, multiplied by speed of light squared, it's the energy released. So looking at the data sheet, what can we see here? U. I'm thinking. Okay, everything's given in U. The mass is given in U. Okay. So then that means we can't use the rest energy values that are given in. Interesting. We can kind of use the rest energy values given in the beginning of, no, on the second page of the equation sheet, top left. If we like or we can use U to calculate E, then calculate convert E into mega electron volts. That's also because all the answers are given in MeV. But basically, first I'm going to start by finding the difference in mass between the two sides. So I'm going to add up this one and this one, right? This one and this one I'm going to add up, and I'm going to see, wait, mass has to be lost for energy to be released, right? I'm going to, from the addition of these two, I'm going to subtract this one. Let's see what we get. How many U's have been lost? 13.00007 plus 1.00728 minus 13.99925. That gives me 8.1 times 10 to the power minus 3 U, right? I'm going to take a shortcut here. I know that the rest energy of the proton, well, a proton has a mass of approximately 1 U. So I'm not going to bother converting this into like putting it into equals mc square, getting it in joules and converting it to mega electron volts. I'm going to use a shortcut. I know that one proton is approximately 1 U, and that corresponds to approximately 940 mega electron volts. So I'm going to figure out how this many U, how much energy corresponds in mega electron volts, because this will give me the answer in joules, right? I don't want that. Times 740, around 7.6. Yeah, I think slightly less, slightly more. Oh dear. So there are two answers that are very much alike, which means the examiner wants us to suffer and do the equals mc square. So yeah, I'm gonna have to do it. Sad. So 8.1 to the power minus 3 times 1 U. U is equal to 1.661 times 10 to the power minus 27. So that's in kilograms now. This mass times C, 3 into 10 to the power 8, whole thing squared. Point 617 times open 3 joules 1.6 1.21 times 10 to the power minus 12 joules. Now we turn the joules into mega electron volts. 1 mega electron volt means 10 to the power 6 times 1.6 into 10 to the power minus 19 joules. So essentially 1.6 times 10 to the power minus 13 joules is 1 mega electron volt. So I'm going to divide this number by 1.6 times 10 to the power minus 13. 7.56. Okay, so this was the answer. Cool. Moving on. The equation represents a typical nuclear fission reaction. Which statement is not true? Let's figure out what's happening. A neutron is colliding with a uranium nucleus, making it unstable and making it break into pieces, releasing 3 more neutrons. Which statement about this reaction is not true? The mass of uranium let's go through this bit by bit. I think 146 La has the greatest binding energy per nucleon of the 3 nuclides. The binding energy per nucleon curve looks like this. It goes up, it peaks, and then goes down. This is iron, Fe. uranium is somewhere over here. This x-axis is mass number. Yeah. It's mass number or nucleon number, I can't quite remember, but anyway, it doesn't matter. Uh, Basically, uranium will be here, and this is 235, right? Anything that's smaller, so La is going to be here. I don't know where Br is going to be. I can't remember whether Br is before iron or after iron. Don't have a periodic table to confirm either, but let's see. 146 La has the greatest binding energy per nucleon of the three nuclides. I don't think so, because this bromine, chlorine, bromine. I think about the periodic table, the top is fluorine, chlorine, bromine, iodine. Iron is in the transition metals, so somewhere here, isn't it? Maybe bromine is somewhere here. I'm not sure. So there's a case for saying that this has the greatest binding energy per nucleon. Maybe, right? Let's take a look at this one. Mass of uranium-235 is greater than the sum of the masses of this and this. Let's take a look. So this and this, what I can see, everything is balanced out. There's a neutron here. Neutron, there are three neutrons over here. If I cancel one neutron, leave this side with two, right? I can see that uranium is equal to the, well, almost equal. We know that there's some energy loss here, some delta M, because like discussed in the earlier question, mc square, that delta M is what causes the energy to be released, right? Mass turns into energy. So I know that these and this is approximately equal to the mass of this plus mass of this plus mass of two neutrons. So this is true for sure. Binding energy of neutrons released in the reaction is zero. Is the binding energy of neutrons released? Neutrons, binding energy. Binding energy is the energy released when nucleons join together to form a nucleus. So I'm not sure about this one either. My gut says it is zero, that it's true, because normally nucleon energy is when you take nucleons, that means neutrons and protons, and when you put them together, the whole structure becomes more stable, and when something becomes more stable, it releases energy, and that amount of energy released when you put nucleons together to make a nucleus is called binding energy. Or binding energy has another definition. If you have a nucleus that's already together, the amount of energy required to separate this and go into here, that is also, so both ways, like if you go from here to here, binding energy is released. Here to here, you have to supply energy to overcome the binding energy, right? So if it's a single thing, in that case, that has no binding energy. So I'm guessing this is true. Binding energy of this one is greater than the binding energy of this one for sure, because now this curve, y-axis, is binding energy per nucleon. Considering that uranium has 235 nucleons, it doesn't matter that binding energy per nucleon is slightly less, right? Because whatever number here, you are multiplying by 235, whatever number here, you are multiplying by 146. So this one is going to be way higher. So this is going to be true as well. This, therefore, by process of elimination, I think this is going to be false, right? True. I'm going to mark that. Let's check the mark scheme really quickly. I'm curious. Oh yeah, it is A. Cool. But you know the logic now, right? 5.6 kilowatt hours of energy released when 1 kilogram of wood pellets are burned. What's the mass lost in? So I think this examiner is a mass lost. Okay. This is such a stupid question, because Yeah, you can't even give a question like, because we know that some of the mass becomes carbon dioxide and so many dumb things, but actually if you look at it, this is energy. This energy c square. So energy and mass lost, when they say, my brain immediately thinks of equals mc square. Delta m is equal to the energy divided by c square, converting 5.6 kilowatt hours, kilowatt 10 to the power 3, 1 hour is 3600. So this gives me the energy in joules. That divide by 3 into 10 to the power 8 whole thing squared. Answer 10 to the power 3, 100, open bracket 3 into close bracket whole thing squared. 0.24 into 10 to the power minus 10. Right? Nuclear radius of an element with nucleon number x is r. What is the nuclear radius of an element with nucleon number y? What's the logic here? Let's check the equation sheet. Size of an electron, radiation, half-life, nuclear radius. There we go. We have an equation. R equals R naught, a to the power 1/3, atomic number to the power. Cool. Nuclear radius number, nucleon number, A, Z. Okay, so not the number of protons, but the number of nucleons. Cool. So I know that I'm going to write as two simultaneous equations. First, I'm going to write for nucleon number x. That's R equals whatever this R naught is, unknown value, x to the power 1/3. For y, it's going to be, I'm going to call it R dash, R naught, y to the power 1/3. Two simultaneous equations. I want to get an expression for this. I'm going to do 1 divided by 2, which gives me R dash of R is equal to y to the power 1/3 divided by x to the power 1/3. Subjecting this gives me y over x to the power 1/3 times r, which is this. Moving on. Synchronous orbit. Synchronous means synchronous orbit. Synchronous means same time period as Earth. Synchronous orbit of the Earth has radius r. What does that mean? Planet has mass twice the mass of Earth. Day on the planet is 1/4 of an Earth day. What is the radius of synchronous orbit for this planet? Oh, stupid. Okay. Again, they are talking about two different situations, which is a sign for you to write a simultaneous equation. Okay. Let's see. Radius of synchronous planet. I'm gonna look in the gravitational fields to see if I can find the quick equation for this, because I can derive it from circular motion, but that's gonna take time. Let's see. Unfortunately, there is no equation for time period, so we are gonna have to derive it. So again, circular motion, the key thing is that we deal with the centripetal force. And here centripetal force is the gravitational force. Gravitational force is the centripetal force. That means gmm over r squared is equal to mv. No, I don't want v. I want, because I'm dealing with capital T, I'm going to go for mr omega squared. Simple m gets cancelled. Omega is equal to G capital M, middle one is capital M, outside is simple m, Gm over r cube, right, square root. Omega is equal to 2 pi over T. So you're going to have to do some math here. Omega is equal to 2 pi over t. So t is equal to 2 pi over omega, which means is equal to 2 pi into the inverse of this, r cube gm. You can do that whatever way you want, but as long as you get an equation for t. Or do we want an equation for r? Interesting. Anyway, radius. Okay, unfortunately, I have subjected the wrong thing. So I'm going to have to square both sides and subject r here because we are interested in the radius. Square both sides, t squared, 4 pi squared. Yeah, I'm going to have to write this. T squared equals 4 pi squared r cube over gm. R is equal to cube root of gm t squared gm t squared over 4 pi squared. Yeah, but what am I interested in here? Now they have doubled the mass, 1/4 of an Earth day. So mass and time are the only variables here. G is a constant, pi is a constant. So really what I'm interested in is R is proportional to cube root of m p squared. That's the key thing. Everything else is constant. I don't care about them. Okay. That means whatever we do, double the mass and quarter the time. So I'm increasing a factor of 2 here. 1/4. What? Quarter. Twice the mass, quarter of uh, the time. The quarter is getting squared. Okay. So what do we end up with? Cube root of 2 over 16. 1 over 8. That is half. So r over 2. Asteroid of mass 2 into 10 to the power 7, escape velocity, blah, 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 radius, origin of magnitude of radius of the asteroid, escape velocity. Escape velocity. Escape velocity is the amount of kinetic energy required to shoot something to infinity. So we start from the surface of the planet. Is it from the surface of the planet? No, it's the center of the planet. Because at those scales, this little distance doesn't matter if you're shooting it to infinity anyway. That's very interesting here. Radius. Oh no, it must be from the surface of the planet, right? To infinity. This is infinity. Obviously, I can't draw infinity on this sheet, but this is infinity. So here the energy is 0. Sorry, the gravitational, the potential is 0. Potential energy, yeah, potential is 0 here, and the potential here we'll say is V. So you need to cross this gap. V is equal to the work done per unit mass because it's a gravitational field, not an electric field where it's Q. Where is M? So work done is kinetic energy. Mass is that. Okay, that mass is given. Order of magnitude of the radius of the asteroid V is equal to gm over r is equal to escape velocity is given. Interesting. Half mv squared over m. We don't even need weird. We don't even need simple m. Why have they given it? So weird. Work done per unit mass. Yeah, right. It makes more sense. The work done is proportional to the mass of the object. Odd. I hope my math's correct, but M and M gets cancelled. Simple M gets cancelled. Radius of the asteroid. Subjecting half V squared. Yeah. Subjecting R. What do I have? GM. R goes this way. 2 goes this way. 2GM. 2GM. R over V squared. Oh dear. Okay. Right. This is capital M. Yeah. I thought they have given simple M, they have given capital M. Simple M is the one that gets cancelled. So this one you run the calculation. 2 into 6.11, no, 6.022 into 10 to the power, what is the value? 6 point capital G, 6.67 10 to the power minus 11. Into the mass of the asteroid they are giving 2 into 10 to the power 17 divided by 40 squared. So I mean get the answer, then get the order of magnitude of that. 220 divided by 8337. So 8.337 10 to the power 3. Diagram shows the gravitational field for binary star system consisting of two stars X and Y of equal mass. Equipotential lines are shown as solid lines. Gravitational field lines are shown as dashed lines. Which statement is correct? More work is done from Q to S. No, from Q to S to R. More work is done moving from Q to S to R than moving directly from Q to R. Let's see. Q, S, R, Q to R. That's false because work done is a scalar quantity. It doesn't matter which path you take. It just matters on the initial point and the final point. Right? So that's false. No work is done from Q to R. Equipotentials, no. So they're on different potentials, so work has to be done. So this is also false. Gravitational field strength is the same at R and S. I don't know about that. But anyway, work done from Q to R and Q to S is the same. Let's see. Q to R, Q to S. That is the same. That's true for sure because this potential and this potential the potential difference between these two and potential difference between these two are exactly the same. So this is the correct one. This one is weird. Gravitational field strength. Just because it's a same potential doesn't mean that the gravitational field strength is the same. It depends on the potential versus x gradient. Whatever gradient it is determines the strength, which is equal to epsilon naught. Something to do with capacitor. Okay. Epsilon naught. Capacitors, electric fields should be in the topic. Look for an equation. Electric fields and capacitors. Epsilon naught. I see it in two places. One is in the force between two point charges, and the other one is the equation for capacitance. So, relative permittivity of a vacuum. Relative permittivity of a vacuum is 1, right? Normally, relative permittivity. Actual permittivity is equal to relative permittivity times this, isn't it? But relative permittivity of a vacuum is 1. Yeah, so that's not going to work. The charge stored on a capacitor consisting of two parallel plates of area 1 meter square separated by 1 meter, where the potential difference between the plates is 1V. Let's take a look at that one. It's C equals A, the same Q. Charge Q is equal to CV, that is equal to A epsilon naught epsilon r over, I'm copying this directly from the equation sheet, over the separation, the voltage, let's see, two parallel plates, area 1, so this becomes 1, separated by 1 meter, this becomes 1, potential difference is 1, this becomes 1, let's see. So it depends on the dielectric. So is that cap? The charge is equal to epsilon naught epsilon r product. So it can't be directly equal to this, right? So I'm thinking that's not the case. Work done in moving 2 coulomb charge from infinity to a distance pi meters from the center of a metal sphere that carries 2 coulomb of charge. What are they talking about there? Work done is equal to Q delta V, that is equal to Q times infinity to distance means just the V here, because potential at infinity is 0. Okay, Q over 4 pi epsilon naught R. So work done when moving a 2 coulomb. So this is 2, radius pi. Let's check that out. 2 times center of a metal sphere that carries 2 coulomb of charge. That is also 2. This is 4 pi epsilon. But it can't be, because the work done, epsilon is in the bottom. How can it be? How can it be? Even if this is pi, nah, it's not gonna work. No, so this is also not going to work. So which means this should be the answer. But yeah, let's see. Let's see, force of charge Q. So the force equation. In that, if I make the charge the subject of the equation, what I get is F 4 pi epsilon naught. Yeah, 4 pi epsilon naught squared F. Yeah, it's starting to look like it. Q, simple Q or whatever it is. Q1, Q2, blah blah. 4 pi. Still no. Weird. I must have missed something. Answer is 24. Supposed to be B. Interesting. How come? Oh, okay. You know what I missed? This is a vacuum, right? They didn't say it's filled with a dielectric. So yeah, I should have assumed that it's a vacuum. So this is 1. So Q is equal to epsilon naught. That's why this was the answer. I just checked the mark scheme for this one. So I missed it. Right? Force between 2 point charges is F. Magnitude of each charge is double. Distance between them is half. So this kind of question, you write the equation. F equals 1.4 pi epsilon naught. So the whole thing is a constant. Right? We don't care about this one. Q over R squared. It's telling me basically 1, 2, 3. These are the interesting things. This side we are doubling each charge. That means times 2 times 2. Then the distance is halved. Divide by half but squared. So looking at this factor here, this is 4 divided by 1 over 4, which is 16. which diagram shows the distribution of charge where the electric potential at P and the electric field at P are both zero. Okay, let's see. Since it's a MCQ, there must be an easy way to do it. Okay. So what I'm thinking is cancellation. Thinking about E being equal to this K is 1 over 4 pi epsilon naught. Okay. For ease. KQ over R squared. Is equal to minus KQ. So I'm looking for symmetry here, like cancellation. Yeah, things to cancel out. Now I can see that this is 2q, this is 2q, which means here still they are not going to cancel out. The voltage due to 2q here is going to be double that of the electric potential due to 2q is going to be double, because this is going, it's going to be double of this in magnitude. This one's going to have a potential which is positive, this one is going to have a potential which is negative over here. So this thing will introduce 4, this will introduce minus 2. So the V cannot cancel out here. For those reasons, I'm destroying this. Over here, what I can see is, now you can see here V is proportional to Q, the magnitude. So whatever, if this gives 2V, this will give V and this will give V. These will have a positive V, this will have a negative V. So there is a cancellation here. Looking at E, this vector is going to be, you can see E is proportional to, you can see the radiuses are equal, as in the separation, the R's are equal from here to here, here to here, and here to here. The R's are equal. So E proportional to Q also. Actually, for the other one also I should have mentioned V proportional to Q only if R is constant. Here, this is constant, this is constant. All three are same, equidistant. So yeah, this is going to push down with let's say 2E. This one, oh scheiße, this is going to be attractive. No? This is also going to be attractive, because you have to know that charge, positive charge Q, the electric field strength vectors are going away from it. So this one will go down. This one will, since it's a negative thing, it will attract to this side. So the E is not 0. Yeah, that's a problem. For that reason, this is also not an option. Let's take a look at this one. The voltage due to this one here, since the R's are same, I'm gonna assume this is this one causes voltage of 3V, minus 3V. This one will supply plus V. This one will supply plus V. This one will supply plus V, making the total voltage 0. Cool. Electric field wise, this one will push this way with 3E. This one will, unfortunately, this will also attract with E. This will also attract with E. These two vectors will cancel out, but unfortunately, this one will pull with E, making E equal to 0, which tells me this will be the answer. Let's see. So this one will give 4V, 2V, negative 2V, negative 2V at the center P, right? This one will give positive V, positive V, positive V, positive V. It will cancel out the potential. Let's see, these two will cancel each other's E, because this one will trying to push it this way. This one will be trying to push it this way with 2E and 2E. These two vectors will cancel out. These ones vectors will also cancel out. These ones vectors will also cancel out, giving this is the answer. 27 ion has a specific charge of 7.1 10 to the power 7 held stationed in a vertical electric field on the surface of the Earth. What are the magnitude and direction of the electric field? Let's see. So the ion is like this. This is Mg. So the Q has to be up. Magnitude and direction of the electric field. Since the specific charge is negative, that tells me that the charge on this is negative. So in order to, we know that if there's some electric field E, put a positive Q, the force will be in this direction. The electric field shows the direction of force on a positive charge. So a negative, if it's a negative Q in the same electric field, it will have a force opposite to the electric field strength vector. So that out. So here, since the force is upwards, it tells me that the field direction is going to be downward. So for a negative charge, yeah. So oh dear, these because they are not valid. Magnitude. We can say EQ is equal to mg. So E is equal to mg over Q. Let me calculate that. This is the Q over m. Specific charge is Q over m. So this is equal to G times this Q over m ratio. So 7.1 into 10 to the power 7 is going to be here. So 9.81 divided by that number. (1.38 10 to the power minus 7). So that's this. Which pair of particles has the largest magnitude of gravitational force to electric force, electrostatic force and gravitational force are separated by the same distance? Yeah, that is that's KQQ over R squared divided by GMM over R squared. So essentially KQQ divided by GMM. These are constants, it doesn't matter. So essentially we are looking at the product of Q over the product of M. That is the essential ratio because everything like cancels out. Electron and pion, charge of +1, same charge, QQ over. So we are looking at the grade for this to be largest, right? Largest. We're looking for QQ to be large and MM to be small. So let's see. QQ, helium nucleus has a charge of +2, proton +1. Okay, proton +1, positive +1. I'm just putting the charge as -1, +1, +1, -1. So we can see, looking at the charges, the top of it, this B option is going to be double. The numerator is going to be double. Now let's look at the mass. I have a feeling that the mass is going to have the biggest part to play in this, right? I think this doubling for the charge product means nothing really. So we need to look at this over here. Electron, pion is kind of big, right? So, yeah, we want this to be small. Let's see. But helium nucleus is much bigger than anything discussed here, and proton is a huge. So that's not going to be having a small product of m into m. Proton and a positive pion. So here electron, positive pion, proton and positive pion. This one will win. So this guy is out. Proton and electron again. Oh dear. Proton, positive pion. Pion is Pion is a meson which has two quarks. Two quarks. This one is three quarks. This one has a smaller mass. This product of mass is smaller. What can be deduced about the radius R of a nucleus of gold from the scattering? This must be some sort of must be a value that's in the book somewhere, because I mean I can show you how to calculate this, but for that I would need the mass. Sorry, I would need the the proton number of gold, which is not there in the physics paper, so it must be in the book somewhere. Yeah, no idea. Look it up, right? Graph shows the plot of neutron number against proton number for nuclei. The logic for this, 45 is here. 45 and 115. 50. We are here. RH 45, 115 is over here. Oh, sorry. Neutron number, not the nucleon number. It's a neutron number. So if it has a 45, 115 number of neutrons, it's 15 minus 45, which is 70. 45, 70. We're actually over here. Likely to decay by it has too many neutrons. Too many neutrons, likely to decay by guessing alpha. But confirming with the mark scheme, this is question number C. Wrong. There must be some logic to this. Number of neutrons is greater than the number of protons. Oh yeah, for sure. Because neutron, when it decays to a proton, it has to release an electron. Balance the charges, plus there's something to balance the lepton number. There will be an electron antineutrino as well, but that's not part of the conversation here. But neutrons need to turn to protons, right? Okay, so my bad. So coming to the middle of this cloud, it needs neutrons need to turn to protons, and that's why it emits electrons, which are beta minus particles. That was the answer. How many neutrons does Z have? So we have a bunch of equations. Okay, cool. Okay, we'll have to figure it out using numbers. Neutron has 1, 0, 238 plus 1, 39 on top, 92 on the bottom, 29, 2. Y we don't know. B is 0 minus 1. This is 92. 92 equals 93 minus 1. 239. But this is 239, okay? It's not appearing. Zoom in there. That'll help. 239. So Y has 239, 93. Okay. This is 0 minus 1. Balancing out, this is 94. This is 239. How many neutrons does that have? 239. That makes no sense. I'll go through that again because that sucks. Oh, no, I was actually correct. I was actually correct. I was looking at the nucleon number. I've erased that, but it was 239, 90. Wait, 239 turned into, yeah, it was 239 change. This is also 239. Yeah, it was 239.94. 239 minus 94, 145 should be the answer. Let me just double check it. 31B, yes. Rock sample found to contain the stable isotope lead-207 when it was formed. The rock contained uranium-235, did not contain lead-207. Okay, uranium-235 decays by a series of steps into lead-207. Half-life of uranium-235 is 0.7 billion years. Half-lives of nuclides, intermediate steps are negligible. Sample of rock now contains 1 atom of lead for every 4 atoms of uranium-235. How long ago was the rock? Let's see. 1 atom of lead-207 for every 4 atoms of uranium-235. So a 1 to 4 ratio, which means that earlier it used to be a 0 to 5 ratio, which means now 20% has decreased. Sorry? Yeah, it has decreased by 20%. The amount of uranium has decreased by, wait, I'm thinking, yes, 1 atom of lead, yeah. So the number of uranium has decreased by 20%. So looking at the equation, N equals N naught to the power minus lambda T, N over N naught, N over N naught, looking at the curve here, decrease by 20%. Just 100%, decrease by 20%. So N is going to be 8%. Yeah. N over N naught is going to be, this number divided by this is going to be 0.8. Okay. That's going to be equal to e to the power minus lambda t. Putting log to both sides, ln 0.8 is equal to minus lambda t. In order to find t, I need to know lambda. How do you figure out lambda? Lambda equals ln2 over t half. Now, it is very important to keep the units of t half and t constant, because now lambda, let's say you put the half-life in, now this one is years, right? Then the unit of lambda is going to be per year. So here when you put per year, your time is going to come out in years as well. Okay, this is something to keep in mind for future. ln2 divided by 0.71 billion will give us lambda, but whatever the value of lambda, our value of t is going to be ln 0.8 divided by divide by minus lambda, isn't it? Yeah. So I'm going to calculate it and directly use a calculator answer because I can't be bothered typing it out. Lambda is another fraction. Half-life, which is 0.2 billion. Billion is 9. 228 10.228 billion. So maybe yeah, this one. that brings us to the end of this paper discussion.